should we start? Okay. So maybe we can finish this discussion. I don't know if you had much time to think about it during lunch, probably not, which is fine, of course. But okay, we can finish the discussion, and then you can, I mean, once again, you are very, I encourage you to take a look at the codes and the data, and if you have questions tomorrow or the day after tomorrow, we can come back to this and discuss in more details. But okay, so let's recap a little bit what was this about. So this is a paper from a few years ago by the group of Bill Bialek, and the idea was to use entropy and information to analyze neural recordings of in vitro, let's say, neural recordings of real neurons subject to a stimulus, and here the stimulus is a movie, and the neurons are retinal neurons that react to light. And so the idea is, as I was saying, you have this movie that lasts 26.5 seconds, and you have the recordings of each neuron. Here they analyze each neuron independently. Then you can refine the analysis and also look at couplings between neurons, but for the moment, you look at just one neuron. And you can discretize the spikes in such a way that in each bin, the bin is 10 milliseconds. You put a 1 if there is at least one spike, so the neuron is active, and you put a 0 if there is no spike. So you have this sequence of bits, and you have 120 repetitions of the experiment. So you can look at the variability of the recording from experiment to experiment. As I was saying, they decided to look at a time of 10 bins, so 100 milliseconds, which is, I mean, then we can discuss why this choice, but it's a typical response time. So you look at how the string of bits that you have in 10 subsequent intervals is related to the stimulus that you had at the beginning. So to do so, what they do, they look at these quantities. So in any given set of 10 intervals, you can have one of 2 to the 10 words. So they call W these words. And so what they do is to look at all possible sets of 10 neighboring bins everywhere at any time and at any repetition of the experiments, and count how many times you find a certain word. This gives you P of W. So you do the average of all the possible positions. From P of W, you can compute an entropy, which is just the sum over the 2 to the 10 words of P of W logarithm of P of W. I think here the base is always natural logarithm. And this gives you a measure of the variability of words, how many words you can see. Then you do the same, but now you only look at one given position. So you look at all the words that start at time 0 in bin 0. You have 120. You can estimate the probabilities, and you can get the probability of a word conditioned to a certain time. Okay. What does this give you? This gives you how much variability you have in the response to the stimulus at time 0. For example, if you fix the bin at time 0, you look here. If the response of the neuron was deterministic, what you would see is always the same word. So this probability would assign probability 1 to a certain word and 0 to all the others. Okay? So this is why, before I made a bit of confusion, this is why they call it the noise entropy, this term, which is actually the conditional entropy of the word conditioned to the time, to the stimulus. Because if this quantity is 0, it means that at a given time, you always observe the same word, which means that the response is deterministic, okay? And the bigger is this entropy, the more noisy is the response. So then you can take the difference between the total entropy minus this, and you get the mutual information between the noise, between the response of the neuron and the stimulus, which actually I define the mutual entropy, I define the mutual information as the difference between the sum of the entropies minus the joint entropy, but you can also, if you have two variables, x and y, you can also define the mutual information, it's the same, you can show it's the same as the difference between s of x and s of x given y, okay? So this is really the mutual information. So I hope this is clear. The other thing is you can compare this to the entropy of a Poisson process. So if you have a Poisson process, then maybe I can make some space here. If you have a Poisson process, it means that the neuron is firing randomly, essentially. And what happens is that the probability of having 0 spikes in a certain range delta t is, so if you call sigma equal to 0 the state in which the neuron is inactive, the probability of being inactive is exponential of minus f delta t, okay? And you get this by saying, okay, the probability of being inactive is the product of the probability of being inactive in each. You divide this in many small intervals. Each of these, and this is going to be basically, so 1 minus the probability of being active in each of the small intervals is f delta t over n, because I'm dividing this delta t in many smaller intervals that I send to 0. So the definition of a Poisson process is that you are active with probability f dt, which is this. So with probability 1 minus f dt, you are inactive. And you want to be inactive in all of these states, so it's to the power n. And so when you send n to infinity, you get this, right? So this is the probability of being inactive. The probability of being active is, of course, 1 minus this. And so you can get the entropy of a Poisson neuron of frequency f with bin delta t, which is just going to be minus, if I call this p0 and I call this p1, this is going to be p0 log p0 minus p1 log p1, right? And if you want the entropy per unit time, you are going to divide this by delta t. Okay, so this will serve as a reference. This is the entropy that this is the variability, if you want, that you would observe here if the neuron was firing at random, right? Okay, so then you can take this notebook that you have in the drive folder. You can take the data, you can look at, you can do these calculations. And what you see is what I was showing before, that here I'm plotting the entropy per unit time, so this quantity, and here you take this quantity and you divide by 100 milliseconds, which is the length of the word. And you do a scatter plot of this quantity over the neurons. And on the x-axis, you have the frequency of the neuron. So you take the whole table and you count basically the number of spikes. You divide by the total time and you get the frequency. So what you see here is what I was saying before, is that the total entropy is very close. So this quantity is very close to this, which means that the neurons are not firing at random, because we know they are not firing at random. This is the next step. But still, the variability of the words is close to that of a random neuron, which means the neurons are kind of exploiting all the possibilities to carry information, okay? So these are the dots here, the squares, and they are compared with the Poisson entropy, that is the line. And then the circles, I'm sorry, the symbols are similar, but this is the same neuron. The circles are the noise entropy, which tells you again how much variability you have at a given time, okay? So the difference between these two is the mutual information, and it is found that it's about half the total entropy. So it's linear in the frequency, so the more frequently you spike and the more you carry information in the same time, which is kind of obvious. But if you divide the mutual information by the total entropy, you get something that is very close to 1/2, which was the point of this paper, that about half of the variability is noise, and the other half is related to the information. You can do also an analysis. I mean, if you want to know how reliable these results are, you can study how the estimate of the information depends on the number of repetitions of the experiment that you use. So you can say, okay, I have 120, let's discard some of them and use only a fraction. And this is how the information depends on the number of repetitions. So you see it's converging. It's not really yet converged. They should have done a bit more. But of course, when you do experiments, you have strong limitations on time and money. So of course, at some point you stop. But anyways, you see it's kind of converging. The scale here is not going to 0. So I mean, it's converging to somewhere. And this is how the information depends on the length of the word that you use. So instead of using 100 milliseconds, you could use shorter words. You cannot do longer because at some point the number of possibilities become too big. But if you use shorter words, you see that it's kind of plateauing. Then, I mean, here it looks like it's increasing again, but this could be noise. I mean, it's not totally clear. But anyways, the scale again is quite narrow. So you can think that you are doing something meaningful. Okay, so that was the, okay, then you can do other things, but this is not very, so this was an example of how you can use these concepts of entropy and mutual information to analyze, again, another kind of biological data that are more coming from neural recordings and instead of biological sequences. Do you have any questions on this? Okay. I hope that this means that it's all clear. It could also mean that you're not interested or that you're not understanding, which would be bad, but I take it as a sign that it's all clear. But again, feel free to ask questions at any time. So, okay.
No, okay, I have a question.
Okay. Thanks for breaking the ice.
Yeah, can you explain again how we conclude that half of the signal can be explained by noise and half by information?
Yes. So basically, this is the raw data. Okay. So each line here is one recording of the same neuron, and each line is one experiment, and then okay, you have the columns that are the times. So if the response was perfectly deterministic, all these lines would be aligned. And you see that I mean, there is some reproducibility, but then there is also some variability. So the measure of variability is this one, which is, okay, with a discretization of time and so on and so forth, but this is telling you, if you fix a time, for example, you fix this time here, 7, and you look at the variability of what happens in the next 100 milliseconds, this is measured by this entropy. If there is no variability, this quantity is equal to 0. And otherwise, I mean, the bigger, I mean, the upper bound is going to be 10. 10 log 2, whatever. I mean, it depends on the log. Okay? So, okay. So this is a measure of the noise. And then you measure the total entropy, which is at any possible time how much variability I have, and you take the difference. So the difference tells you, if I know the time, how much do I know about what will happen next, right? Because basically this gives you an idea of how much the words are variable. So at any time, if you pick a time at random, how much do you know about the word that will follow? This is the total entropy, right? While the conditional entropy is how much do you know about the word that will follow if you know the time. So if you know the stimulus. Okay? The difference between, so this is the information. And then this is just an empirical observation that if you divide the information by the total entropy, you get this plot, which is about 1/2. What is it? This one. You get about 1/2 for all the neurons independently of the frequency. Now I don't think they had I don't think there is an explanation for this. It's for why it's 1/2, but it was an observation.
It is 1/2 because?
No, exactly. I mean, no, it is 1/2 just because. Okay, this is.
Wrong formulation of the word. Since it is 1/2, we conclude that.
I mean, what we conclude is that out of the variability of this, so entropy is a measure of how many words you can have, okay? And half of this variability is predictable from the stimulus, and the other half is just noise. That's the conclusion. So basically, if I tell you at which time you are, you can cut by half the uncertainty that you have on what will the neuron do in the next 100 milliseconds. Does it answer? Now, what are the biological implications of this? I don't think that I have an answer, but at least it gives you an idea of how hard it is to extract the signal from the noise. Okay?
Yes. When you say 1/2 is the noise, means that you have 1/2 rule is random, like you don't know if you use the mystic or not, or it's like noise that a kind of signal that you don't want.
I think what it means is that half of the variability cannot be predicted by fixing a time. So if you fix a time, if I tell you at which you are watching a movie and you are looking at what the neurons are doing in response to the movie, and the point is that if I tell you at which point in the movie you are, you can reduce by half the variability. There could be, I mean, what remains, they call it noise, then it could also be related to other processes that are not related to the response to the signal, but okay. Okay. Now, we will come back to similar data later, and we will see also how neurons are correlated and so on and so forth. But so this was just to give an idea of what you can do with this kind of data. Okay, so now we can go back to the inference problem, and so as a first example of an inference method, we can study the maximum entropy principle. Probably you have already used it, but well, we can revisit it and see how it works. So the idea is very simple. So you have some information about the system that is partial. So you have a random system. So you have a random variable x. And you would like to estimate the probability distribution of x that you don't know. So up to this point, I was assuming that you know the probability distribution. Now I'm assuming that you don't know it, but you have some partial information. And this partial information could be, for example, that you measure the average of something. For example, you could measure the average of x. So maybe you know the average, or maybe you know something else. And so the question is, what is the best probability distribution that is compatible with the information that you have on your variable? So the idea, I mean, you can answer this question in many ways. So the maximum entropy principle is not the unique answer to this question. It's one possible answer, so it's a principle, it's not an axiom. So the idea is to say, okay, because entropy is a measure of the uncertainty that I have about my variable, I will try to maximize it in such a way that I'm doing the least, I'm being the most agnostic as possible. I mean, I'm trying to make the least assumptions on my variable, okay? So the idea is I introduce the entropy, H, and I want to maximize the entropy, but now subject to the constraints that come from the information that I have, okay? So for example, I might try to maximize the entropy while fixing the average of the variable to a certain value, okay? So how do I do this? I want to maximize this quantity over p, so the unknown here is p, and I want to impose this kind of constraints. So in order to impose the constraints, I use the method of Lagrange multipliers. That, do you know the method of Lagrange multipliers? You do? Okay. I assume you do, and if you don't, let me know, we can discuss. So the recipe is just you want to maximize a function subject to constraints. So what you do, you add here what is called the Lagrange multiplier, which is a real number that multiplies the constraint. So what are the constraints? This one is a constraint. So for example, the sum of p of x times x should be equal to mu. But we also have the constraint that the probabilities should be normalized. So we have to impose that the sum over x of p of x should be equal to 1. So we put a multiplier lambda 0 to fix that. And then we add the multiplier lambda 1 to fix that sum over x of x p of x must be equal to mu. So the recipe is that we call this Lagrangian. This will be a function of p, the vector of the probabilities, and of the lambda that is the vector of Lagrange multipliers. You will have one multiplier per constraint. And what you have to do, according to the Lagrange multiplier method, is to take the derivatives of L and set them to 0. Okay? And well, this is it has a geometric interpretation that is quite easy, and again, it's in the book, and I'm happy to discuss it if you want later. So if you take the derivatives with respect to the lambda, of course, for example, if you take the derivative with respect to lambda 0 and you set it to 0, you get this, that this quantity should be equal to 0, which is the constraint you want to impose. So this part, this one gives you the constraints. What is more interesting is this part. So if I take the derivative with respect to p of x, here what I get, and okay, the other thing is it doesn't really matter if we maximize the Shannon entropy or the Gibbs entropy because they're proportional. So let's drop this 2 from the logarithm, just to avoid having log 2 everywhere. So when we take the derivative with respect to px, here we get minus the derivative of p log p, which is log p minus 1. And then we get, here we get 1 when we take the derivative with respect to px. So we get lambda 0 from this term plus lambda 1x when we take the derivative here. So this should be 0. And we get then that p of x, so we bring the log on the other side, and we get that p of x is the exponential of this term. Okay? So we get what is called an exponential distribution. The distribution of x that we are looking for is the, plus, right? Plus. Is the exponential of something, where this something is a constant, plus the Lagrange multiplier lambda 1 that multiplies x, where x is the quantity we want to fix. So now we have to find lambda 0 and lambda 1. And to find lambda 0 and lambda 1, we have to impose the constraints. So how do we do that? First of all, we want to impose that the sum over x of p of x should be equal to 1. So to do this, we can rewrite this as a product of exponentials. This is a constant. So of course, this constant must be the sum of this one. So by imposing the normalization, we get that p of x should be exponential of lambda 1x divided by the sum over x of exponential of lambda 1x. So in this way, we fix the lambda 0. Sorry that the blackboard is over, but. And then we have to fix lambda 1. And to fix lambda 1, we have to use this equation. So we have to impose that sum over x of x times exponential of lambda 1x divided by the normalization is equal to mu. So this will be an implicit equation for lambda 1 that you cannot solve in general, but then you have to specialize to what you want to do. And you get, then if you can solve it, you solve it. Otherwise, you solve it numerically, and you get lambda 1. Okay? So this is the idea. Now, you can generalize this idea to more complicated constraints. So if you have, okay, maybe I will rewrite it from scratch. Is it clear up to this point for everyone? Okay. If you have many constraints, you can say, okay, I have functions of x, ga of x, and I want to fix the averages of these functions to some numbers that I call g bar a. And I have many of these. This can be x, x squared, x cubed, something else. How do I generalize this? Well, I can just write here sum over a of lambda a, sum over x of ga of x minus g bar, right? So before I had two multipliers, lambda 0 and lambda 1. So here I have a sum from, I don't know, 1 to a, where capital A is the number of constraints that I have. From 0 to a. Where lambda 0 is still the normalization, so I can always choose g0 of x to be equal to 1, right? Then then this corresponds to the normalization. It tells me that the expectation of 1 should be 1. And then I have the other multipliers. There is a p of x here missing. Okay. So now we can do the same. We can take the derivative with respect to p. And what we get is minus log p minus 1 plus the sum of lambda a g a equal to 0. Right? So again, the distribution p of x that maximizes the entropy is an exponential of minus 1 plus, now I write it explicitly here, the sum is from 0 to a, but we can bring the 0 term outside, so we get minus 1 plus lambda 0 times g0, that is 1, plus the sum over 1 to a of lambda a ga of x. Okay? So this is, in general, the maximum entropy distribution. And once again, these multipliers must be determined by fixing the constraints. So when you fix the normalization, you can do the same trick as before. You factorize the exponentials. So now this is a constant. And so this constant must be equal to have the normalization to the sum of this other term. So, sorry if I erase, but it's easier. You just get this, and in the denominator you have the sum over x of the numerator. Okay? And you can do this for any choice of the GA. So this is what maximizes the entropy. Now, maximum entropy distributions have a certain number of nice properties. So, okay, the statement here is just that, so if you want to maximize the entropy with a set of constraints, you obtain an exponential distribution, which is the exponential of a linear combination of your constraints, normalized, where these terms are obtained, must be obtained by fixing the constraints. So now, what are the nice properties of these distributions? The nice property is that the denominator, I mean, you already know from statistical physics that the denominator of this quantity that you can call partition function. So, okay, well, let's write it here. So if I call z of lambda the sum over x of the exponential of the sum over a of lambda a ga of x, then this quantity generates all the cumulants of, the logarithm of this quantity generates all the cumulants of the g. What does it mean? That if I take the logarithm of z and I do the derivative with respect to 1 of the lambda, this is going to be 1 over z times the sum over x, let's call this b. So when I take the derivative of the log, I have 1 over z times the sum times the derivative over z, which is the sum over x of this, times the derivative of the exponent. So I get just g a of x. And this is exactly the expectation of g a with respect to the probability distribution, right? Because this is the maximum entropy distribution, and here you have GA that multiplies this in the numerator divided by the denominator, which is the partition function. So if you take derivatives with respect to the lambda, you generate the expectations that you have to fix. And if you take more derivatives, you generate the covariance. So for example, if you do the second derivative with respect to lambda A, lambda B of the log of Z, you have to take another derivative of this, which will give you 1 over Z times the derivative here, which will bring you another factor of G. Here, let's call it C. So this is when you take the derivative with respect to lambda here, and then you have to take the derivative of Z. So you get minus 1 over Z squared times this. So I don't rewrite it. Times another derivative of Z, which will give you another factor like this one, but this time with B. So please stop me if I'm going too fast, but I assume that you might already have seen this thing. So this quantity, the second derivative, is going to be the expectation of GA, GB minus the product of the expectations of GA times GB. So it's the covariance of GA and GB. And if you keep taking derivatives, you will generate all the cumulants of the G. Okay? So this is a nice property of the maximum entropy distributions, also called Gibbs-Boltzmann distributions, that once you know the denominator, you take derivatives and you can get all the averages of all the G that you are fixing. Okay? Fine. Now, the fact that the matrix of the second derivatives of the logarithm of Z is the matrix of the covariances has one important implication, which is the following. So in order to find the lambda, we would like to solve these equations, right? If we have 10 constraints, here the sum over A goes from 1 to 10, and we have 10 constraints, so we have 10 Lagrange multipliers and 10 equations, and we have to solve this system of 10 nonlinear equations for the lambda. This seems complicated, right? But it's not that complicated. Why? Because the expectations of the G are the derivatives of the logarithm of Z. So what we would like to do is to impose that the derivatives of the logarithm of Z are equal to these numbers that we want to fix. And at the same time, we know that the second derivatives are the covariances. So well, let's erase this. Now, the matrix of the covariances has a property that is a positive definite matrix. Okay? Why? Because if I call this matrix, let's call it, I don't know, M, A, B. If I take any vector, V, and I do V, A, M, A, B, V, B, and I sum over A, B, what do I get? I have to multiply by VA, VB here, and I have to sum. So what I get is the expectation of G dot V square. Right? Here I get G times V, and I have to sum, so I get a dot product twice, minus the expectation of G dot V square. So this is the variance of G dot V. So it's a positive quantity. So this means that this matrix M is always positive when I apply it to a vector V, and so it's a positive definite matrix. Why this is important? Because this means that the function log Z is convex or concave. I mean, whatever. Concave, right? When it's like this, it's concave. Convex. Whatever, I can never remember. Anyways, it has a definite concavity. So, why this is useful? Because I can introduce a new function. Let's call it k of lambda, which is the logarithm of z of lambda minus sum over a of lambda a g bar a. Okay, where g bar a are the values of the constraints I want to impose. And the equations that determine the lambda are simply that the derivative of k with respect to lambda a, which is equal to the derivative of log z minus g bar, should be equal to 0, right? Because I want to impose that the derivative of log z is equal to g bar. So I have to find, in order to solve the equations, in order to find the lambda, I have to find a point, a stationary point of this function k. But the second derivatives of k because this term is linear in lambda, the second derivatives of k are the same as the second derivatives of log z. So they are equal to MAB. So again, the function k is convex as the function log z, or concave. Okay. So in order to, in order to find the lambda, we have to find the stationary point of a function whose second derivative is always positive. So we have to minimize, we have to find the minimum of this function. And this minimum, because the function is convex or whatever, is unique. Okay? So we have to minimize this function, find the point where the derivatives are 0, and knowing that the matrix of the second derivatives is a matrix of covariances, so it's a positive definite matrix. So how do you do that? Well, you have to minimize this function. It's convex, so you can do gradient descent. So if you do gradient descent, what you will do is to initialize the lambda at random, for example, or as you wish, basically, because the minimum is unique. And then you can say that lambda a k plus 1 is equal to lambda a k minus the gradient So you iterate this a certain number of times with small enough eta, and then you have to be careful to converge well. Maybe you have to reduce the learning rate a little bit during the learning, but you know that this will converge to the minimum of k. So this will give you, after a certain number of iterations, this will give you the lambda, okay? So the good thing about maximum entropy, and this is true in general, is that you can always, you have the guarantee that you can find the multipliers, even if the problem of finding the multipliers looks a bit complicated, because you have to solve this set of coupled nonlinear equations. You can always do it by this procedure, and this is called Boltzmann learning. This procedure, basically, the procedure of doing gradient descent on this function kappa. Okay? Yes?
Can you please explain again, how did you say that matrix M is always positive?
Yes.
Why that variance is always
So okay, is it okay up to this point, or should I repeat this as you prefer? I mean, so basically, okay, the idea is this. I can tell you the logic, and then you can tell me where you want more details. So I start from k, and k is the logarithm of z. And z is the normalization of the probability. So the probability that maximizes the entropy has the form exponential of this divided by z, and z is the sum of the numerator. Okay? So now I define this function k. If I take the derivative of k, when I take the derivative of log z, I get 1 over z times the derivative of z. When I take the derivative of z with respect to lambda a, I get a GA here. So the derivative of log z is equal to the average of GA over this distribution, right? And so this term is equal to the expectation of GA minus G bar A, and this is what I want to be 0 in order to fix my constraints. If I take another derivative with respect to lambda b, I have to take the derivative of 1 over z times the sum of the exponential of lambda g times g. So I do another derivative, and I will get this. Okay? Now, why this is positive definite? Because so the definition of a matrix being positive definite is that v, for any vector v, if you choose a vector v as you want, for all v, you must have that v times m times v should be positive. Okay? So if M is a matrix of covariances, then when you do sum, so this means that you have to do a sum over AB of VA, MAB, VB, right? And so when I do this, what I get is sum over AB of VA expectation of GA, GB times VB minus the same thing with the product of expectations. Okay? So now I can bring the V inside. And when I do the sum over A, I get V times G. So this is the expectation of V dot G square, where here V is constant and G is a random variable, because G is a function of X that is a random variable, minus the expectation of, here I get, this is V, this is the expectation of V dot G, and I get it twice. So this quantity here is the variance of a random variable, and the random variable is V dot G. Now we know that variances are positive. Just because, you know, if I call this, if I call y equal to V dot G, G is, X is a random variable, G of X is a random variable, Y is a random variable, and this quantity is just the expectation of Y square minus the expectation of Y square, which is positive by, I mean, you complete the square, and this is going to be also, you can write this as the expectation of Y minus the expectation of Y square. So it's the expectation of a square which is positive. Okay? So for any vector v, the matrix M contracted with the vector v is the variance of something, so it's positive. Okay, so to recap what we have done up to this point, we have said, okay, I have a system, I have some random system. I don't know the probability of the states of my random system, but I know the averages of some quantities. For example, I know the average of x, or maybe I know the average of x squared, and so on and so forth, because maybe I can measure these quantities. So what I want to do is to infer a probability distribution for my system using this information. And what I do is I maximize the entropy. Why? Because I know that maximizing the entropy means I try to maximize the uncertainty on my system. And so I'm doing the least possible assumptions on my system other than the things I know. Okay? So when I maximize the entropy, I get this form. I get an exponential. More specific, I get an exponential of a linear combination of the quantities I want to fix. This is called an exponential distribution, or in statistics, or a Gibbs-Boltzmann distribution in physics. And it has the nice properties that the second derivatives of the logarithm of z are positive, and the first derivatives fix the constraints. So it means I can find the lambda by doing this gradient descent process. Okay? Now, in order to get a little bit more familiar with the idea, I wanted to show one example, a very simple example. Two examples. I mean, one is a blackboard calculation, and the second I will show you some data. So the blackboard calculation is the following. It's another little kind of problem related to games. So I suppose that there is a I suppose that there is a casino and there is a game that is being played. So the game is very simple. There is a die, a six-sided die that gives results 1, 2, 3, 4, 5, 6. Okay, and you at each time the croupier, let's say, rolls the die, and you get a value of x. And so if you want to play, you have to pay one coin to play, and then you win. What you win is a function m of x. So if you get 1 or 6, you win 0. If you get 2 or 5, you win 1 coin. And if you get 3 or 4, you win 2 coins. Okay? So if the die is a fair one, and all the states have probability 1/6, this is a fair game, right? Because with probability 1/3, you lose a coin, because you pay 1 coin to play. So with probability 1/3, you lose it. With probability 1/3, you win a coin. And with probability 1/3, nothing happens. You get back your coin. Of course, the game is not fair because the casino has to make money. So what is the gain of the casino? Well, in this case, the gain is 1. This is the gain not of the player, it's the gain of the casino. So this is the gain. If the result is 1 or 6, the casino wins a coin. Otherwise, if it's 3 or 4, it loses a coin, and otherwise it's 0. Now, so you are a player, and you want to play the game, and you don't know what is the probability of the results, because you don't have access to You cannot observe the game long enough to have an estimate of the results. But what you know, because the casino has to pay taxes, you can look at last year. I'm sorry, it's a very idealized setting, but okay, just to give an idea. So you can look at last year, and what you know is that last year the casino has won 400 coins. Okay. And you also know that from some other information that 7,000 players have played the. So you can say, okay, the average gain last year was 4/70. Okay, so it's a small gain per play, but non-zero. So based on this, you can use the maximum entropy, and you can say, okay, if I want to have an estimate of the probabilities of the values of x, I can try to maximize the entropy with this constraint, right? So what do you get? What you get is that the probability of x, this is the function g that I want to use in my constraint. So I will get exponential of lambda g divided by the sum over x of exponential of lambda g, right? So my estimate of the probability will be p of x will be exponential of lambda divided by z, where z is the denominator, 1 over z, exponential of minus lambda over z, and well, it's symmetric, so the other ones are identical, right? And I have to fix lambda. So in order to fix lambda, what do? You have to impose that the sum over x of g of x, p of x is equal to 4/70. What is this? This is going to be 2 exponential of lambda minus 2 exponential of minus lambda, because I have, in this case, I have two cases where the gain is 1 with probability exponential of lambda, two cases where the gain is 0, and two cases where the gain is minus 1, divided by 2 plus this, okay? The 2 goes away. And you get an equation for lambda that you can solve. I skip the details, it's not very important. What is important is that in the end, the probabilities are the following. Here you get something like 0.18. Here you get something like 0.16, and here you get something like well, let's do this. Let's put one more digit just to say that, whatever, okay. So what is interesting, I think, here is that you see that the probabilities are as close as possible to the uniform one, which would give 1/6 to each state, which is 0.16. And so the idea is that really you can use this also if you're the casino. You can use this same idea to design your game in such a way that you make a gain, but with the smallest possible bias, by biasing your game as little as possible with respect to the uniform distribution, which would be the unbiased result. Okay? So the idea of the maximum entropy is really to try to find the least biased distribution that achieves the results that you want to get. In this case, the gain that you want to get. Okay? Is it clear? Okay. So this is a little example. Now, a more interesting example where you can see the interest of this method is, okay, and then we will apply it also to biological data, but later. Now I wanted to show you another little tutorial that is taken from the first book, the one that is not yet published. I closed it. What's going on? Okay. So in order to illustrate this idea, I took a data set of football games. So what I want to show here in this tutorial is that the maximum entropy principle allows you to obtain reliable estimates of your probability distribution even when you have few data, okay? Which is typically the case in biology. In biology, you never have a lot of data because experiments are still quite expensive. And so the idea here is to show that if you have few data but a good model, you can still have meaningful information on the parameters of the model even if you have few data. So, okay, the data set is a set of results, so you can download here from this link the results of international football matches from 1872 to 2017. So you have 50,000 matches, which is a lot, between national men's football teams. So the idea is to try to make a model for the results, for how many goals a team will score in a given match. And so the idea is that we want to do this with few data. So the idea is to have a good model. So the idea is to look at the data and also have some intuition on what's going on. And okay, again, this is an illustration and not pretending that this is reality. It's also, I have a very poor understanding of football, so I don't, but it's just to give you an idea of how it could work. So you could say, okay, maybe I could split the matches in 3 categories. Bad matches where I don't know, my team is very weak against, and the opponent is very strong, so I have no chance of scoring a goal. Normal matches that are typical somehow, and then very good matches where either my team is in very good shape or the opposite team is particularly weak, and then I do a lot of goals, okay? So based on this idea, you could say, okay, from my data, I could estimate 3 quantities. The probability of scoring 0 goals, which is more or less the probability of a bad match. The average number of goals, that is, it gives me an idea of the typical situation. And then some measure of the probability of having many, many goals, which I took here for convenience. You could imagine other measures. I took the average value of the goals in excess of 10. Okay? So this is the expectation of x minus 10 times the indicator function that x is bigger than 10. So this is 0 if x is smaller than 10, and 1 if x is bigger than 10. So you define 3 quantities, 3 of these functions g, that characterize the 3 situations you want to discuss. So bad matches, typical matches, and very good matches. Okay. And then what you can do is to say, okay, maybe I can try to construct a maximum entropy model where I constrain these 3 quantities. Okay? Is it a good model? So, okay. First of all, to give you an idea, so now once again, if you want to play with this data, you can go to the drive folder and you can get the code, or you can try to write your own code and have a look at the data. So here you see, this is how the data look like. You have, each row is a match, This is like Scotland versus England in 1872, 0-0. And then you have more recent matches like from 2025. Okay, I don't know why I wrote 2017 here. I don't know, it was a mistake. Anyway. This is the number of matches, and then you can just extract the number of goals, and you can do what you want. So this is how it looks like. This is the histogram of the number of goals that a team can score in one of these matches. And this is in log. The y-axis is in log. And this is a Poisson distribution. Okay, so if you just say, okay, you could say, okay, maybe it's a Poisson distribution. I just fix the mean. So I compute the mean. From the mean, I can estimate the Poisson distribution, and this is the black line. So what you see two things. First of all, that there is a tail, much bigger than Poisson, which is the situation where your team is very strong. And also you see that you don't get very well the probability, this is in linear scale, you don't get very well the probability of 0 matches. So this is the reason why you could think, okay, maybe I can try to add something to describe the tail and the small x. Okay, so if you do that, what is the maximum entropy distribution? I don't know if you can read, but the maximum entropy distribution, as I was saying, is the exponential of a linear combination of your constraints. So the constraints are the indicator function of 0 goals, the average, which is x, and then the indicator function of more than 10 multiplied by x minus 10. So why, the reason I chose it in this way is that it's easy in that case to compute the partition function because these are geometric sums. So you do your calculation and you get this result. Okay? So you have 3 Lagrange multipliers that you have to fix. And in order to impose the constraints, what you have to do is to take the derivatives of the logarithm of the partition function that you have and impose that these derivatives are equal to the averages that you can compute from the data. Okay, you have to solve the equations. You can do Boltzmann learning, or you can, in this case, it's easier to just take a solver of nonlinear equations. You can check in the code. And this is what happens. You see that this time it works quite well. You can get a good fit. I chose it that way, and this is why I say, you need a good model. So, and well, both in log scale and in linear scale, you can get a good agreement. Okay, why is this interesting? This was done with all the data. So I have 50,000 matches. In each match, there are 2 scores for the 2 teams. So I have 100,000 data. But I can repeat the procedure, and I can do it on a subset of all the data. So I can take at random m matches, and I can look at how things change when you change the number of data that you have. So what I show here is these are the values of the 3 quantities that I defined, G1, G2, G3. So G1 is the probability of 0 goals. G2 is the average number of goals. And G3 is the probability of an avalanche of goals, like more than 10, essentially. It's the number of goals in excess. So what you see, what I think is interesting to observe here is that even with very few data, you already get a good estimate, because these are averages, and we know that averages converge fast because of central limit theorem. So the results are very stable. Here is with the 100,000 matches, and this is with few matches. Like this is 2 to the 10, I think, so it's 1,000, and then you increase. And so you see, if you do maximum entropy with few data, or with many data, the results are stable enough, provided you have a good model. This is not, I mean, depends on your model, but if you choose a reasonable model and if you're lucky that the model is a good model for your situation, then even with very few data, you can get decent estimates. And just to give you an idea, this is what you would get with 2,000 data. If you do a histogram, the tail is impossible to guess from this, right? And still, if you do maximum entropy, you can get a decent estimate of the slope here, because the lambda, as I was showing before, are stable enough. And the lambdas are what control the tail of the distribution. So this is just a simple illustration to show the idea. So the idea is when you have few data, it might be a good idea to compute some average, some macroscopic information from your data, and then try to guess the right model. And if you are smart enough or lucky enough, then you can get good insight on your problem. So even with few data, you could get a reasonable estimate of the parameters that enter in the distribution. Okay. So I think this is what I wanted to say on this problem. Okay. Is there any question on this part? I'm going fast with respect to what I expected. So, but if it's clear, then we can move to the next part. If I go fast, it means I can also add something later. So it's okay. Okay, so to recap, this maximum entropy principle is a useful tool in inference based on this idea of maximizing the uncertainty compatible with some information you have on your system. Now, can we do something else? So again, if we want to infer a probability distribution from data. Yes, we can do many other things, and one thing we can do is Bayesian inference that you have already seen, I think, many times probably, but in particular over the past 2 weeks with the course of Mauro and Bruno. So you have probably you are already very familiar with it, but just to recap, Bayesian inference is based on Bayes' rule, which is the following. Is there any? So let me think. Should I? Well, I want to give you an example that I like. It's very easy. Probably you have already seen it, but let's do it. Let's do it anyways. So, okay, Bayes' rule is the following thing. You want to estimate the probability of some variable y conditional to some observation x. And the way you do that is to use the definition x. And then you use here that the probability of x and y is also given by the probability of x given y times p of y divided by p of x. Okay, and so the idea is that so x is something you observe, and y is something you want to estimate, but you reverse the problem by writing it in terms of the probability of observing x given y times some probability of y, and then normalized. So in Bayesian inference, this is called prior, and this one is called likelihood. And this one is called posterior. Why these names? And this is why I want to illustrate this example. So these names, so this example is adapted from the book. There is a similar example in the book of Nate Silver called The Signal and the Noise. That is a book about Bayesian inference. I think it gives an idea of why you're doing this. I think really the idea here is that you have, this is called prior, because the idea is that before you do any observation, you start with some belief about y. And P of y is your own idea of what y could be. So you start by assigning a probability distribution to the values of this unknown object y. Then, after you have formed your prior belief, you receive some evidence, some new evidence, in the form of some data. Okay? So x are the data that you get. And P of x given y, which is called the likelihood, is again your own model of how the data are formed, are generated, given y. Okay? So there are two ingredients that you have to fix. You have to decide what is your belief, your prior belief on y, and you have to decide what is the model that you make of how data are generated if you know y. These two things are choices you have to make. Given this, the interesting aspect of this relation is that it gives you a quantitative recipe to update your belief, right? So if you make a model for P of y and P of x given y, and you use this, after you got information x, you can update your model. So this would be your new model. Let's see the example. This is the example that we put in the book. So there has been some theft, so someone stole something, and Alice is a detective. Alice is the detective, and Alice suspects that Bob is the culprit, the one that stole the item. Okay. Now, so the first thing that Alice does is to make a prior model. Okay, so she will say, okay, I think that Bob is guilty with probability. So there are two states for y. Y is the state of Bob, which is, let's say, y equal 1 is that Bob is guilty. And y equal 0 is that Bob is innocent. Okay? So Alice will start by a prior belief. So she has some information or some, I don't know, prejudice on Bob. So she says, okay, with 95% probability, I think that Bob is guilty. And with 5% probability, I think that Bob is innocent. Okay. Now she's about to go and arrest Bob because the probability seems high enough. And she receives a phone call from someone that we will call Claire, just to keep the ABC. So Claire calls Alice and says, well, you know, the night that this thing was stolen, I was actually having dinner with Bob. Ah, okay, so now Bob seems innocent. But the thing is that Claire could be lying. Maybe Claire is a friend of Bob and she wants to give an alibi to Bob, and so she's lying. So now we have to do the calculations. The thing is that now we have the probabilities, the prior probabilities, and now we have to make a model for the likelihood that Claire is telling the truth. I mean, no, sorry, for the likelihood that Claire is telling that she had dinner with Alice. X equal to 1 is what you get as information, which is Claire says she had dinner with Bob. the night of the, okay? So what Alice needs to do is to make a model for P of this event given Y, okay? So there are two possibilities. And now, again, now this is in the hands of Alice. She has to make a model. So I want to stress that this will not, these things are not given to you by some external principle. You have to make a model for them. So just to follow the book. So let's say if you have two possibilities. One is that Bob is guilty, okay, and Claire is lying. So you will get the probability that, so Claire says she had dinner with Bob, but she might be lying. Given that Bob is guilty. And then you have the probability that Claire is telling the truth. Well, or I always get in trouble, but you have the probability that Claire is lying, and given that Bob is guilty, and you need the probability that Claire is telling the truth. Given that Bob is innocent. Okay? So you make a model for this. How would I make a model for this? I would say, okay, if Bob is innocent, there is no reason for Claire to lie. So I would say the probability that Claire is telling the truth given that Bob is innocent is 1. If he is innocent, why would she lie? On the other hand, if he's guilty, then there is a certain probability that Claire is lying because maybe she's a friend of Bob. Let's say, just to follow my example, that Alice trusts Claire. So she says, okay, the probability that Claire is lying is low. Let's say 0.15. 15%. Now with this, Alice can update the belief. How do you do that? Well, the probability now that the probability of Bob being guilty, given the information you got, which is that this one, is given by what? So in the denominator, you have P of x. P of x is the probability of this event, right? So P of x will be equal to the sum over y of the numerator. So this will be, with probability 95%, Bob is guilty. So you get 95%. And if Bob is guilty, the probability that Claire is lying is this one, right? Plus the probability that Bob is innocent, which is 5%, times the probability that Claire will tell you that she had dinner with Bob, given that he's innocent, which is 1. So this will give you some number for P of x. And then the probability of Bob being, what do we want, guilty, for example, will be just this term, which is the probability that Bob is guilty times the probability that Claire is covering him, divided by the denominator. And this one is 0.74. So you see that now Alice, so before she got the phone call, Alice was quite certain, quite confident that Bob was guilty. Now she gets the phone call, she makes a model, and under the model, she can update the belief, and now the probability that Bob is guilty is down to 74%. This is the probability that y is equal to 1, given x. Okay? So you can be quantitative, right? You can update your belief in a quantitative way, and then you can decide whether 75% is enough to arrest Bob or not. And the point is that basically this is going down because Alice trusts Claire quite a bit. Okay, then it depends on this number how much it goes down. But the power of this relation is that you can be, after you have done a model for your prior belief and for the likelihood of the data that you receive, you can be quantitative on how you update your belief. And the other powerful thing is that you can iterate this, because now it's down to 74%, and maybe there will be another phone call, or maybe you will find another piece of evidence, and you can update this number again in light of new evidence, and you can keep going until you reach a decision, okay? So what I would like to do next, tomorrow, is to show you how we can apply this to a few problems, and how this is connected with the maximum entropy, because it is because the maximum entropy is a special case of this. And then one important point will be that if you have enough evidence, so if you iterate this process enough times and you have enough data, the initial prior that you had will fade away, okay? So if you are in a good setting, which is called asymptotic inference, where you have many data, this posterior will converge to something that, I mean, okay, if you have, yeah, will converge to something that something good, independently of the prior that you have. So in principle, if you have enough evidence, you can forget your own prejudice, which seems good. So maybe we can do this tomorrow and stop here for today. And again, if there are questions, I'm happy to stay and discuss.